Hey guys, in this video we're going to have a look at simplifying some more complex surd equations, and we'll do a few examples to show you a few techniques and different circumstances you may encounter. In a previous video we went over some basic surd equation simplification, so this is supposed to be a little bit more complex. So let's get into it. These are the questions which we're going to go through. So let's start out with the first. Simplify root 3 times root 6. So remember from a previous video when we went through the basic surd law, which says that root xy can be represented as root x times xy. So that's basically the most important thing to remember as we go through these examples. The other thing to remember is to almost treat these surds as variables, and we can use some of the similar algebraic operations that we've gone over previously, as well as some basic surd simplification techniques. So those are the main things to be aware of when solving these examples. So let's have a look here. So root 3 times root 6, we know that we can represent this as root 3 times 6, which of course gives us root 18. Now we want to try and reduce this so that we can pull out an integer out the front of the surd. And remember in a previous video I talked about trying to relate this value in the surd to one of these integer squares. So you want to look at 1 squared, 2 squared, 3 squared, 4 squared, etc. So you'll see here, if we go through those numbers, 19 breaks down fairly well into 18 breaks down into 9 times 2. And of course, root 9 can be represented as 3. So in this case, we're left with 3 root 2. And that's how we got there. And that's our solution for that one. All right, next one we're going to have a look at is question 2. And that's going to be 5 root 6 times 2 root 3. So in this case, we want to pull out everything outside of the surds, still outside the surds, and we're going to pull everything under the surd, under a single surd. So here we end up with 5 times 2 outside the surd, which gives us 10. And of course we're left with 6 times 3, which is 18 within the surd. And exactly the same as our last question, we can break this root 18 down to root 9 times root 2, which of course gives us 10 times root 9 is 3 outside of root 2, which gives us our solution, which is 30 root 2. And that's our answer for that one. So you'll see you'll end up with a few common surds, and once you know what to do for each of those, break it down into the integer squares, then it sort of gets a lot more straightforward to simplify. So next question here, question 3, is root 2 all outside of 3 root 2 plus root 3. So if you're thinking, oh, this looks a little bit different to what we've seen so far, recall that it's actually very straightforward. It's exactly what we need to use here is exactly the distributive formula that you would have seen when solving algebraic equations. So we just need to multiply the first term out through the rest of the components. Plus root 2 times. So here I've multiplied root 2 by the first component, 3 root 2, and then added root 2 multiplied by the second component, root 3. And this is what we're left with. And by moving this apart or breaking this out, root 2 times root 2. So first let's take the 3 out, and we're left with root 2 times root 2 plus, let's simplify root 2 times root 3 all under root 6, as we know using our law. So interestingly, when we have root 2 multiplied by root 2, or when we multiply the same surd by itself, these surds disappear, Why is this? Let's have a quick look over here. So root 2 is equal to 2 to the power of a half. And so root 2 multiplied by root 2 is 2 to the power of a half multiplied by 2 to the power of half. Just write a couple notes here. By 2 to the power of a half, or 2 to the power of a half squared, or using our index law, 2 to the power of a half times 2. And of course, a half times 2 is 1, 2 to the power of 1, which leaves us with 2. So that's why multiplying a surd by itself results in the number within it. So here we're left with 3 times 4. So root 2 times root 2 is 2. Sorry, not 2. Not 4, it should be 2. And plus, that's our first term, plus our second term, which is still root 6. We'll get to this in a second. So it leaves us with 6 plus root 6. And root 6 we know we can break down. In fact, we can't break down root 6 any further. Why is that? Because the factors of 6 are 1, 2, 3, and 6, and none of those are the result of squaring any integers. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and already we've passed all of our factors of 6. So this is our final solution, 6 plus root 6. So next question now, question 4 is 2 root 7 plus 5 root 7. And this one you should see straight away that, like when we add different algebraic terms, the answer here is just going to be, we've got 2 lots of something plus 5 lots of that same thing. We're left with 7 root 7. And there's no way to simplify that any further. Why? Because 7 can't be simplified into any of the integer squares, because, as you know, the factors of 7, just 1 and 7. So that's our solution for that one. So next one, question 5. Let's say 5 root 3 plus root 27. So in this case, 5 root 3 looks pretty simplified, but root 27 definitely isn't. So when you have 2 terms with different surds, it's a good idea to try and represent them both in terms of the same surd, so that you then can combine or do something with them. So let's try and represent root 27 in the form of root 3. And if you think about it for a second, it's actually fairly straightforward. Why? Because 3 squared is 9, and 9 is a factor of 27. It goes into 27 3 times. So, whoops, that's supposed to be 9. So root 27 can be broken down into root 9 times root 3. And having a look at this further, we can reduce root 9 to 3 root 3. And we're left with 5 root 3 plus 3 root 3, which of course, like in our last example, we can combine to 8 root 3. So that's our 5th example, that's the solution. And let's have a look at our final example now, which will require a little bit more working. And that's, oops, inside the brackets we have 2 root 5 minus root 2, that's inside one set of brackets, and inside a second set of brackets we have root 10 minus 1. And similarly to the third question we looked at, we can use the distributive law here to expand out these brackets to get a few different components. So first we have the first component in the first brackets multiplied by first component in the second bracket. So we have 2 root 5 times root 10. And then we subtract 1 times 2 root 5, so minus 2 root 5. Then we subtract root 2 times root 10. And lastly, we add minus and a minus, 1 times root 2 plus 1 times root 2 is 2. So the next thing we can do is simplify this using our law up top to 2 outside of root 50 minus 2 root 5, and simplify this brackets 2 minus root 20 plus root 2. So let's have a look at now simplifying surds where we can. We realize that we can't simplify root 5 or root 2, both in their simplest forms already, but we can definitely simplify root 50 and root 20. Root 50 simplifies to 25, root 25 times 2 times root 2. These middle terms, or this middle term will leave by itself. Root 20 simplifies to root 4 times root 5. And we're left with plus root 2 at the end. Now the reason that you can, when you're simplifying a series of numbers with different surds, you want to try and, as I mentioned before, group together similar surds. So here we had a 2 root 5, so you can see that maybe another term is going to result in a root 5, as the third term did. And likewise, we had a root 2, which means that one of our other terms might result in that as well, which it did. We got our 2 root 50 down to something similar. So let's just carry on working. Root 25 is 5, and we're left with 2 times root 5, 2 times 5 or root 2 minus 2 root 5 minus, and then simplifying this component here, we end up with 2 root 5, and we're left with plus root 2, and finally simplifying everything once again, we're left with 10 root 2 minus 2 root 5 minus 2 root 5 plus root 2, and lastly, just combining like terms, we're left with 10 root 2 plus root 2, 11 root 2, minus 2 root 5 minus 2 root 5. Well, that just leaves us with minus 4 root 5. And that's our solution. So you see we had to play with this one a little bit more, but we didn't do anything too complicated. We used mostly our variable operations that we've used in algebraic equations, as well as the basic surd simplification rules, including this one. And that's all we had to use to break down something that looks fairly complex into just a couple of simple terms. So that's it, guys. Thanks for watching. I hope you enjoyed, and catch you in the next video. Thanks. Bye.